Hello, everybody. Hey, this is going to be our lecture for week 6, lecture 1. It's going to be pretty short, and it's going to involve helping out with the question of the day for Monday, the 16th of November. But it's also just some more applications of Newton's second law and drawing free body diagrams. All right, so we have a concept in this section called equilibrium. And equilibrium, as it implies, is that we have equality. So in this case, it's going to have equal forces in all directions. And that is going to give us one of two situations. We could have static equilibrium, or we could have dynamic equilibrium. Now, as the names imply, static means not moving and dynamic means moving. Now, we had a little bit of this last week in week 5, in which when we were drawing free body diagrams, we are setting up a convenient XY coordinate system. And very often when we had this situation, we had our block, which we know is if it's going to slide, it's going to go up and down the thing. So we're going to make that our X, and therefore our Y was going perpendicular or normal to that. And when we set it up that way, we can realize that physically that block is not going to sink into our inclined plane, nor is it going to levitate away from it. So we set up in this situation, we knew that the sum of the forces in the Y was equal to 0, and that is an example. That's an example of equilibrium, and in which, in the y direction, there was no acceleration. Now, we could have this block. If we had this block move down where its velocity is constant, okay, if that velocity is constant, it is moving, but there is no acceleration, and that's an example of something called a dynamic equilibrium. Now, in a static equilibrium, as if we have a couple things that are just couple ropes, for example, that are holding up a mass and they are at various angles, okay, then that is not moving, and that is what we call a static equilibrium. Now, if these are ropes, strings, cables, chains, that sort of thing, okay, then we end up with having what is called a tension, okay? And those ropes, strings, cables, chains, etc., provide tension when they are pulled, when they are put under tension. And when you pull, you're going to pull left and right, okay? So within a rope, okay, you're going to have a tension to the right and a tension to the left. Left, right. Okay, now if this is attached to something, okay, that means this rope right here is pulling this object to the left, and if there is another object, then it is going to be pulling this to the right. So we can see that this tension in the middle, okay, is going in both directions, and if this is static, not moving, it is as if these two objects are touching each other. And so that tension in the middle is just kind of the in-between. So it's kind of the bridge saying that there is going to be a push or a pull directly. Okay, now they could also be moving, and there could be, these things could be accelerating, they could be accelerating together. They could be accelerating together. And if they are accelerating together, we still have tension, okay? But in that case, it will not be at equilibrium. And we will see an example of that on Tuesday, the 17th. You'll see another short lecture. All right, so let's go back. Let's go back to this bottom one as an example. And there is, in the question of the day, for Monday the 16th, there is something that's going to be similar. So I'm going to do this example. So let's see that we have a rope that is going to be attached to a 12 kilogram object, and we're going to call this tension 1, and you've got another rope that's attached to it, which we're going to call tension 2. And we're going to say that this is 45 degrees, and we're going to say that this is 30 degrees. And we're going to say that this whole thing is not moving. So that means when we get to the point in our problem solving where we have the sum of the forces is equal to ma, we're going to have the sum of the forces equal to 0 because everything is static, not moving. All right. So in our directions on how to draw free body diagrams, the first thing is to put or have a convenient XY coordinate system. So in this case, we're just going to have it the normal horizontal and vertical being X and Y. And we can now draw that free body diagram. And I'm going to kind of just superimpose it. I'm going to superimpose it on our diagram here. So right here, we're going to have this force right here, which is T2. And we're going to have that force right there, which is T1. Those two things are touching it. It is like an applied force. Everything that touches it plus gravity, okay? And the force of gravity is going to go straight down. And essentially, that's it. We have no friction because it's not moving. All right. So now we can, our next step there is to resolve any vectors that's not going in our X and Y direction. And we can see that T1 is not going in either the X or the Y, so we are going to break that up. And so when we break it up, we're going to have a component that is going up, and we're going to have a component that's going left. So this one right here is going to be T1 sine 45. Okay, that's the part that's pulling up, and this one up here is going to be T1 cosine 45 degrees. We're going to do something very similar on the other side. We're going to have a portion of T2 sine 30, and that is that one, and then we're going to have T2 cosine 30, T2 cosine 30, which is at the top. And now essentially we've gotten rid of these, and now everything is in our X or Y, and now we can apply Newton's second law that say the sum of the forces is equal to ma, but as we talked about already, it's not moving, so we can say the sum of the forces in the Y direction is equal to 0. And we can also say the sum of the forces in the X direction is equal to 0. So when we do this, okay, I'm going to say to the right is positive, and I'm going to say T2 cosine 30 degrees minus T1 cosine 45 degrees, and then that is equal to 0. Okay, now since they are going to subtract and add up to 0, then we can set them equal to each other. So we know that T2 cosine 30 degrees is equal to T1 cosine 45 degrees, okay? And that gives us one of our equations. And we can also have, over here, we're going to have the sum of the forces. Sorry, this up here was in the X direction, sorry. Now we're going to do the Y direction. So in this case, we're going to have T1 sine 45 going up plus T2 sine 30 going up. Now going down is going to be the force of gravity, which is equal to mg, which is equal to 12 times 9.8, which I believe is equal to 117.6. And we're just going to call that 118 newtons. 118 newtons is our force of gravity. And these two are going up, and that's going to be minus 118 newtons. And and that's going to equal to 0 because they're not moving. Now, we're going to take this 118 and bring it to the other side, making it turn positive, and now we're just going to have equals. So now we're going to have two equations with two unknowns. We got this equation and this equation, and as we know, when we have a system of equations, we need as many equations as we have unknowns, which we have, and we're going to solve for those, and we can solve for those by adding and subtracting, which I don't think works conveniently here, and we can do a substitution, which works fine. We found out last week or the week before that we could end up with a situation where we might have to graph it and solve for our zeros in order to get our answer. But in this case, we're going to do substitution. So if we look here at the top, I'm going to say T2 cosine 30 degrees divided by the cosine of 45 degrees, and that's going to equal to T1, okay? So right there, we're going to divide both sides, and now we've isolated T1. And if we do the cosine of 30 divided by the cosine of 45, then we can get a number here. So we're going to say cosine of 30 divided by the cosine of 45, and we're going to end up with 1.22. So 1.22 T2 is equal to T1. And now we're going to substitute. We're going to substitute this wherever we see T1, we're going to replace it with this 1.22 T2. Okay, so now we're going to have our T1 times the sine of 45 degrees plus T2 times sine of 30. Now we're going to substitute in here. We're going to have 1.22 T2, and now we're going to have T2 sine 30 is equal to 118 newtons. Now we can break this down. The sine of 45, is going to be 0.707, so we're going to take this 1.2 times the sine of 45, and it's going to give us 0.866. So we're going to have 0.87 T2 plus 0.5 T2, because the sine of 30 is 0.5. When we add those two together, 0.5 plus 0.866, plus 0.5 gives us 1.37. So we're going to have 1.37 T2 is equal to 118 newtons. Now we can divide both sides by 1.37, and 118 divided by 1.37 gives us 86.1. Okay, so T2 is equal to 86.1 newtons. We'll call that 86. Now we can multiply. We can multiply this 86 times 1.22, and we can get T1 is equal to 86 times 1.22, and we're going to have 105.08. So this is going to be 105 newtons. And these are our two tensions in there, and we have solved for the tension of this static equilibrium problem. All right, so very similar to our question of the day for Monday, November 16th. So have a look at this, take notes on it, and we'll be seeing these same concepts in the future. All right, take care until next time.